And we can also come back to a paper later if there are questions arise. Okay, so Georg is still not here, right? Are there any questions from the speakers, or is everything clear? Okay, I guess you've seen some sessions already, so you know more or less what to expect. So, oh, Georg is here. Hello, Georg.
Yes, hi, I'm here.
Can you show up so we check that you're visible? Okay, great. We can also check if the screen shares correctly. Can you share your screen?
Yes, that's a good idea. One sec. Okay.
Okay, I can see myself, so it looks fine.
Okay, now you should see my screen. Can you see my screen?
Yeah. Okay. Okay, I guess we can get started then. Is everybody set up? Okay, so welcome to the questions and answers session of ICALP track B, session E4. So we will start with our first speaker, Alan Logan, who will be presenting the paper on the post correspondence problem and equalizers for certain free group and monoid morphism. Please, Alan, the screen is yours.
Okay, sorry, I was trying to unmute myself. So hello, thank you for coming. I'm assuming you've all, well, at least read the abstract. So, okay, this is joint work with Archie Bano. There we go. Okay, so the paper addresses two problems. So firstly, the post correspondence problem, which is relatively classical. So, well, here it is stated you've got given two morphisms, G and H, is the equalizer of them trivial. These could be free group morphisms or free monoid morphisms. Free monoid morphisms have been studied since the 40s, but free group morphisms have not been. So it's undecidable if you're for free monoid morphisms, as Post proved in the 1940s, but it's unknown for free group morphisms. A second related problem is, can we describe the equalizer? So the same input, you're given a pair of morphisms, and does there exist an algorithm which will somehow describe the equalizer? So in the talk, I talked about if it's free monoid morphisms, you would maybe want a regular automata, a finite state automata, which would accept the equalizer as its language. But for the free group case, you would be wanting a free basis. And again, the same duality exists. The problem is known to be undecidable for free monoids, even if you assume that such an automata exists. And in fact, this was proven by the author of the third talk just now, Alexei Sarila. Yeah, but again, it's open for free groups, and this was a problem stated in the 80s by Stallings. Okay, so these are the problems that we addressed in the talk, but we didn't address them in full generality. Instead, we addressed them for marked morphisms and for immersions of free groups. So here I said a set is marked if all the letters begin with all the words begin with a different letter. So here, both words start with different letters. The first one starts with X, the second one starts with Y. Therefore, this is a marked set. So a morphism is marked if the generators are marked. And an immersion is marked because immersions are about free groups. We have to care about inverses. So you instead of just caring about the image of the generators, you care about the image of the generators and their formal inverses. So here is an example of a morphism. So A goes to xy and B goes to yxy. The set xy and yxy is marked. So as a free monoid morphism, this is a marked morphism. But as an immersion, it's not marked. And the reason is because you care about inverses. I mean, you can just think of inverses as being, as sort of reversing the word. So it's a bit like saying they have to start with different letters and also end with different letters. And here they're ending with y, both of them. So you don't get an immersion. Okay, so hopefully that's relatively clear. So our theorems are that the two problems that I mentioned earlier are decidable for both immersions and for marked morphisms. So yeah, the AEP, the algorithmic equalizer problem, is soluble for marked morphisms and for immersions. And also you get this cool result that the rank is bounded. The rank of your equalizer is bounded above by the rank of the ambient free group or free monoid, which addresses another question of Stallings for the free group case. Yeah, so that's a brief summary of the talk, stroke the paper. Any questions?
Thank you very much for the talk. So we have a question for from Pengfei Yang through Slack. I'll read out the question.
Sure.
Thank you for your interesting talk. As you mentioned in the main theorem for immersions in the free groups or monoids, the equalizer can be represented. The equalizer of a set can be represented as the image of some marked morphism. Moreover, there is an algorithm to compute the marked morphism if S is finite. My question about this is it possible to give the time complexity of the algorithm and of computing this image?
Okay, so by a remarkable coincidence, I wrote a slide which explains exactly the answer to this question. The proof of the marked PCP, so the PCP for marked morphisms was known to be decidable from about 2000, and they give a space complexity of n cubed log n, and this gives you a time complexity of 2 to the power of that. It's missing a big O, but anyway. So for the marked AEP, you actually get a worse complexity. It's your space complexity is 2 to the n, so then your time complexity is 2 to the 2 to the n. But there's a very specific reason for this. Here's the picture I had in the last slide, which took me a day to create, so I figured I should reuse it just now. The process of the algorithm is you're moving left. In this picture, you start with these two morphisms G and H, and then you compute G1 and H1, compute G2 and H2, and so on. For the marked PCP, all they care about is when this algorithm terminates, they look at the thing that they get. But because we're trying to compute a basis, we actually have to store each of these maps, G1, G2, G3. And you can see the last line. So at the very bottom I've said the PCP is the question. When you terminate, you just check the basis elements to see if the equalizer of the corresponding thing is empty. But for the AEP, you have to you take the corresponding set and then you compose that with all the maps you computed. So you had to store those maps before, and there's exponentially many of them. So that's the reason you get such a high space complexity.
Okay, thanks. There's a question from Joel. Joel, maybe you can ask your question.
Hi, yeah, thanks. So I was wondering, there is a paper from 2009 by Paul Bell and Igor Potapov, where they consider a problem called the identity correspondence problem.
Sure, yeah.
I would imagine this is very closely related somehow to the PCP for free groups that you define. I was wondering if you thought about sort of simple reductions between the two. Is it a consequence of that paper that PCP for free groups might be undecidable, for example? Is that something that could follow an easy way, or can you say something about why it's difficult to move between the two?
So, right, the reason it's difficult to move between the two is because they're assuming that everything is positive. So essentially they're taking a map. So I suppose the answer is I can't quite remember.
Okay, yeah, no
but
problem.
the problems are inequivalent.
Okay.
Although they're related, but they're slightly tricky.
Okay.
And I should maybe mention that it's actually that if you could manage to extend the PCP from free monoids to free groups, you would actually be addressing the AEP rather than the PCP.
Okay.
For whatever reason.
Okay, thanks very much.
Yeah.
Okay, Alan, thanks a lot. There's some other questions to this paper. Maybe we can postpone them until later because now we have to move to the next paper, which will be presented by Moses Canardi and will be on the complexity of knapsack problems in wreath problems. So Moses, please, you can start.
Okay, so I hope you can see my screen.
Yes.
So this is joint work with Michael Figelius, Markus Loray, and Georg Zetsche. And I will just briefly outline what wreath products are, what we mean by knapsack problems, and what our main results are. So wreath products are a construction from group theory, how to combine two groups. Here in this case, let me give you the example of the group of integers and z squared. So how you can imagine this is you have the infinite grid, which is z squared, and then you have a finite labeling of the points with integers, which is the left part z. And then additionally, you have a cursor which points to some of the cells in the of some cell in the grid. And then you have two kinds of operations or generators. The first one is you can move around in the cell to adjacent neighbors, or you can manipulate the current cell by adding or multiplying some element. And in this paper, we consider wreath products where the right group is Z. So this is like some kind of one-dimensional version of this picture. Then we also consider iterated wreath products of free abelian groups. So these groups look very complicated. And this is actually also the main result, the main motivation why we study wreath products, because you can study free solvable groups since they can always be embedded into these iterated wreath products. Okay, so if we get some results for these iterated wreath products, we also get them for free solvable groups. So we want to solve two decision problems. The first one is the knapsack problem, which is the problem given elements G1 to Gn and H from the group. Does this equation have a solution? So are there non-negative numbers xi such that G1 to the x1, G2 to the x2, and so on is equal to H? And this has been studied for various groups. And well, this is a generalization of Diophantine linear equations, where this is basically the problem over the group Z. And a related problem is some kind of evaluation problem of this sort, which we call the power word problem. So here you're given elements G1 to Gn and numbers K1 to Kn, which are in binary, so they can be exponentially large. And the question is whether G1 to the K1, G2 to the K2, and so on equals to 1. But the connection is you can show that knapsack for a group is in NP if you can prove an exponential bound on the solutions of solvable knapsack equations, and additionally show that the power word problem is in polynomial time. And this is what we do in this paper for these particular groups. So the main theorem says that knapsack is an NP for wreath products of G with the integers, where G is any finite nilpotent group, and also for iterated wreath products of free abelian groups of some fixed iteration depth. And this is shown by first showing that there's an exponential bound on these solutions, and then showing that the power word problem is in polynomial time, in fact in TC0 for the groups as I've mentioned above. And so in fact, we also get the same results for free solvable groups. Okay, that's my summary.
Thank you very much. So we have two questions from Engel Leforcheux through Slack. What about the knapsack problem where the exponents are in the integers instead of the naturals?
Yes, the naturals, so the version with the natural numbers is harder, or conversely, you can always reduce the integer case to the natural number case because you can like replace g to the x by g to the x and g to the minus y, and so you can simulate an integer by natural numbers. So we solved the harder problem, but I think it's still open whether there's a reduction in the other direction.
Okay, and the other question is as follows: you rely on recurrences that seem to have constant coefficients. What class would be obtained if allowing polynomial coefficients in the recurrence, also known as holonomic sequences?
So I think what he's referring to is, so we introduced some kind of notion of linear recurrent sequences for nilpotent groups. So what you do is basically you define a sequence of group elements where every group is defined as a product of previous elements. And in a certain sense, you can view them as polynomials. So I'm not sure what the question is pointing to. But I'm also I don't know what these holonomic sequences are.
In holonomic sequences, well, there are experts here, but I understand that the coefficients may depend on n, which is the number of the element of the sequence, and they can depend polynomially on those elements. Correct? I'm wrong. Somebody from the audience, please.
Okay, yeah.
I don't know if the question will make sense in the context in your context.
Yeah, I'm not sure. So I'm not familiar with that concept. Yeah.
Okay. Maybe somebody else wants to comment or ask a question referring to this paper. Laura?
Yeah, thanks. I was just wondering, this is a very open-ended general question. Can you compare and contrast to the membership problem? So submonoid membership problem or subgroups and membership problem? Because you're close, but in terms of decidability and complexity.
Oh, yes. So I think there are other people who have a better overview over these results, but I know that there are various groups where these, where, for example, Knapsack is decidable, but other problems are not decidable. So, but to be honest, I don't have the overview for which groups this is the case or not.
Okay.
For example, one result that I have in mind is for the rational subsets. I think they quickly become undecidable for these wreath products. So there's a paper by Markus and Georg and Ben Steinberg, I think, on that.
Yeah, so maybe I can comment on this. So the first type of groups here, G, wreath, Z, so their rational subset is decidable, but as of now, the complexity is not known. It's they're only non-primitive recursive algorithms. And for the iterated wreath products, we know it's undecidable. So if you take Z wreath Z, then rational subset membership is already undecidable, as is submonoid membership. So Knapsack is typically much, much easier. Mm-hmm. So for people who do verification, this is somewhat related to flat systems, which are sometimes considered, where so if you consider general reachability in infinite state systems, this is similar to rational subset membership, but flat systems where you have a sequence of loops and want to decide reachability there, that corresponds to Knapsack. So there you also have this phenomenon that the flat case is much, much easier, both in decidability and complexity.
Okay, thanks.
Okay, we have time for a brief question if there's or comment. Anybody that's willing to ask something, please raise your hand. Or Flora? Yeah? No? Okay. Yeah, okay. I guess we can move this case to the next talk by Alexis Sarela about hardness results for constant free pattern languages and word equations.
Okay, hello everyone. I'll just start the screen share in a minute. Okay, so very quickly, this paper has three main results. First, I proved that the inclusion problem of non-erasing pattern languages is undecidable, even in the case of constant free patterns. And the idea here is that we can start with patterns with constants, because for them this problem is undecidable, and then we can replace the constants by these new variables a and b. And then we add some prefixes and suffixes to the patterns in a certain way, and then everything will just work. The second result is that the non-periodic satisfiability problem of constant free-word equations is NP-hard. And here the idea is that we start with a system of equations where the only constant letter is 0, because we know that the satisfiability problem is already NP-hard in this case. And then we replace this constant by a squared b squared, where these a and b are variables. And then we add some very simple equations to the system, and this will be a quite simple reduction. And the final result is that a variant called the non-commuting satisfiability problem of constant free-word equations is not only NP-hard, but it's polynomially equivalent to the general satisfiability problem. And here the idea is that we start with a system of equations with constants, and we replace the constants with certain more complicated words over these variables a and b, and add some slightly more complicated equations to the system. So this is a bit more complicated than the previous result. So this was a very quick summary of the results. And now I'm happy to answer questions.
Thank you very much. We have some questions posted via Slack, but by Joel and by Marcus, but they're here, so maybe they can ask the questions. Maybe Marcus, you can ask your question.
Okay, yeah, thanks, Alexi. It's a nice video presentation, very clear. Congratulations for that. I was wondering, could you describe what is the basic intuition behind the different decidability statuses of this inclusion problem for the constant free pattern languages? I mean, what's the crucial difference underlying these problems?
Yes, so if we look at the particular construction here, for example, well, in general, if we look at the erasing pattern languages of constant free patterns, and if there is some variable that appears in the pattern only once, like for example, if here in this v prime pattern we have the s and some other variables which appear only once, then we can just map everything else to the empty word and this one variable to any word. So the pattern language will actually contain all words. So these erasing pattern languages of constant free patterns are limited in this sense, that either they are the whole sigma star, or we need to use every variable at least twice in the pattern. And this is a big restriction. So the same idea I have used here does not work in the erasing case at all for that reason, for example. Mm-hmm. But in general, if we look at this table, well, I proved that this problem here is undecidable for the non-erasing case, this constant free inclusion problem, and the erasing case is decidable. So here the non-erasing case is the more difficult. But on the other hand, if we look at the equivalence problem for the general patterns, then the non-erasing case is easy, while as the erasing case is still open. So it's not at all clear which one of these is the easier one, the non-erasing or the erasing case. It kind of depends on the problem. So this is in general very, very interesting.
Mm-hmm. Okay, thanks.
Okay, so thanks. And we have a question from Joel. Joel?
Yeah, so I think that explanation leads me quite nicely into this. So it's kind of clear that the reduction that you give doesn't work for the erasing case, as you just explained. However, it did kind of make me think when I was looking at your paper that maybe there is a possibility to prove that the inclusion problem in the general erasing case is decidable by providing another reduction that maybe is not the same, but essentially does the same job. Because if you could produce such a reduction, then because we know that the constant free case is decidable, then the general case should also be decidable as well. Have you thought about that at all, or are there any results which would say that such an approach is not possible, or do you have any thoughts or comments on that?
Well, yes, the idea certainly came to my mind that if we could prove a reduction here, then we would indeed get the result that this this last open case is decidable. But this is more more difficult in two ways. So the fact that we are considering erasing languages instead of non-erasing, and the other difficulty is that we are considering the equivalence problem instead of inclusion problem. So I think both of these will make it more difficult. So I only spent a very little time thinking about this, and it seemed that these difficulties are too big, or at least I immediately did not see how this reduction could be proved. But maybe it's something that should be examined or studied a little bit more to see whether there is anything to be proved here.
Thanks.
Okay, thanks. Are there any other questions? If not, then we can move to the.
Sorry, could I quickly ask a question?
Sure.
You had these numbers of variables, some lower bounds of how many you need to get undecidability, and you mentioned this as an open problem in the paper. But how? I mean, where do these come from in the Bremer-Freidenberger paper?
I should probably take a look at this Bremer-Freidenberger paper before I could answer this question.
Okay.
So somehow from that paper we get this fairly large 2,554, and that then very simply leads to the bounds in my paper, but I can't here answer where this 2,554 comes from.
Yeah, I mean, I can check that myself also. Thanks.
Okay, thanks a lot. If there are any questions, you can just speak up or raise your hand. There's a button for raising the hand. It's in the reactions. Sorry, it's not in the reactions. Where's the button?
It is down there. You just don't see it because you are a co-host.
Oh, okay. Yeah. So everybody can click a button. There's next to in the panel at the bottom, there's a reactions button, and there's a raise hand, and then I can see that you raised your hand. But you can also just unmute yourself and ask a question now or in the following papers. So if there are no other questions, then we can move to the next paper. So Florent will be presenting the paper on weakly-unambiguous Parikh automata and their link to holonomic sequences. Please, Florent, you can start.
You can see my screen?
Yes, we can.
Can you?
Yeah, you can. We can see your screen. You can start. Thanks.
Okay. I'm not sure if I'm getting a stable connection right now. I don't know. But...
So there seemed to be a bit of a lag, but maybe it's gonna. Well, maybe you can turn off your video. Maybe that will help, because this might be eating up the bandwidth. Well, now we can't hear you, I think. Can you say something, Florent?
Connection right now.
Okay.
Did you hear what I was saying?
No, we didn't.
You didn't?
I didn't.
All right, but sorry.
What you're saying now, so maybe you can try saying something.
Okay. All right, so I just started by presenting myself. So I'm a PhD student under the supervision of Arnaud Carriol and Cyril Nicot, and this is a joint point with Aline Bostan, Arnaud Carriol, and Cyril Nicot. And what we did in our article was to study the link between formal languages and combinatorics through the generating series, which basically counts the number of words of each length in the language. So it's a formal series sum over all n of ln z to the power of n, where ln denotes the number of words of length n in the language. And it is well established that regular languages have rational series. unambiguous context-free languages have algebraic series. This is a Chomsky-Suter-Blaget theorem. And what we wanted to do is to extend this hierarchy of languages and series. So there is a natural way to extend the hierarchy of series on the right with holonomic series, which are series satisfying a linear differential equation with polynomial coefficients. And equivalently, the sequence satisfies a linear recurrence with polynomial coefficients. And what we wanted to do is to find in the automata model a class of automata that corresponds to holonomic series. When we look at their generating series are holonomic. And this is the class, so the class we exhibited is the class of weakly-unambiguous push-down Parikh automata. So a Parikh automaton is just like an automaton. You have states, you have letters, and you have vectors. And when you read a word, you read the letters by concatenating them, and you add the vectors that you are seeing. And the word is accepted if in the end, the sum of the vectors you have seen in the transitions belong to a final semilinear set C. And to be able to make the link between the language behind the automaton and the way you describe the automaton, we need a notion of unambiguity. And so we call the Parikh automaton weakly-unambiguous if every word accepted by the automaton has only one way to be accepted. You can only find one run in the automaton that is an accepting run that accepts the word. So here we depicted an automaton recognizing the set of words that have an A in the middle, and it is weakly-unambiguous because there is only one way to be accepted by this automaton, by taking the middle transition right in the middle of the word. So our contributions rely on this results that weakly-unambiguous push-down Parikh automata have holonomic generating series. And then we derived conclusions, some consequences of this, such as analytic criteria to prove inherent weak ambiguity of push-down Parikh automata languages. We also gave a proof by hand of one case where the analytic criteria failed to prove that it is inherently weakly and ambiguous. And finally, we used the holonomic generating series to find effective bonds for the inclusion problem of two weakly-unambiguous Parikh automata. So we derived the bond of the length of the minimal witness, proving that a language of a weakly-unambiguous Parikh automata is not included into the language of another one. Thank you.
Thank you, Florent. There's a question from Lorenzo. Lorenzo, can you ask the question? Oh, and maybe, by the way, Florent, maybe you can turn on your video now. So maybe this.
Sorry. Okay, but it says I can't start it because the animator stopped it.
You should
okay.
be able to do it now.
All right. Start.
Okay.
Is it? I want to find Zoom.
So Lorenzo doesn't want to ask a question, then I can read it out.
Okay.
I enjoyed watching the presentation, and I have a question about slide 20. We have a doubly exponential upper bound on the length of the shortest witness of non-inclusion, and you claim that it yields a doubly exponential algorithm. Is it correct that it even yields an XP space algorithm?
Wait, yes, for the algorithm, we didn't look at the algorithm in terms of space complexity. So maybe there is, I'm just trying to find slide. Sorry. Right, this slide. Yes, so our algorithm was focusing on time complexity and not space complexity. So the algorithm we provide here is 2 X space. It's not just X space, I think. because basically we are counting the number of words of length up to this bound. And for instance, if the automaton you're looking at recognizes every word, they are of this size. So the number of words of this size is exponential in this bound. So when you are looking at the space of these numbers, you have this double bound.
Mm-hmm.
So maybe there is a way, but the algorithm we provide is not X-space.
Okay. There's also a question from Engel. Engel, maybe you can ask the question, because Lorenzo had trouble with connecting, but maybe Engel will be more lucky. If not, then I can read the question. From what I understood, both weakly-unambiguous Parikh automata and weakly-unambiguous pushdown Parikh automata have holonomic generating series, but do not describe the whole class of holonomic series. Are there specific properties for the class of holonomic series associated to these automata? Given such a holonomic series, can we, in the other direction, build a corresponding automaton, or even simply identify whether such an automaton exists?
Right. So this is a good question. We are working on it, so it's not the class of all holonomic series, indeed. We don't know yet for pushdown Parikh automata, but for just Parikh automata, they correspond to diagonals of n rational series. So it's not the whole class of holonomic series.
Mm-hmm.
For pushdown Parikh automata, we don't know yet. We haven't studied this. But...
Okay, Georg, you wanted to ask a question? Go ahead.
Yeah, thanks. So I have a question about the model. So why did you choose pushdown Parikh automata? Is that because that's the most powerful model for which you could show that the resulting series is holonomic, or are there any other reasons?
Yes.
I see. Okay. And then I have another question about terminology, if I may. There is a paper by Alain Finkel, Michael Cadillac, and I believe Pierre McKenzie, where they look at unambiguous Parikh automata. And it seems to me that your definition is exactly the same, or is there a difference?
No, there is difference. So that's why we said weakly unambiguous. Sorry. There is a slide where yes, here. So the definition of Cadillac, Finkel, and McKenzie, they asked for the automaton without the vectors to be unambiguous.
Oh, I see.
So here, if you suppress the vectors, this automaton is not unambiguous.
I see. Okay, I see.
Because you can take in every A in the word can take this transition.
Yeah.
And
I see. Okay.
And typically, the language we put here, words with an A in the middle, is not recognizable by an unambiguous Parikh automaton in the sense of Cadillac, Finkel, and McKenzie.
Mm-hmm. I see. Okay, thank you.
So Lorenzo, Laura has a question. Go ahead.
So just wondering, how are your languages? Where do they fit in other hierarchies? Are they indexed? How do they compare to blind mental counter? Because there's results about some of those having holonomic series.
Okay, can you repeat the question? Sorry,
So your languages that have, it's hard for me to say the whole name, Weakly-unambiguous, right? So are they indexed, for example?
I don't know, to be...
in the hierarchy of languages.
I know that corresponds to unambiguous reversal bounding counter machines.
Okay.
But indexed, sorry, I don't know exactly the definition of languages, so...
Okay.
So perhaps I can answer. I don't believe they're indexed. So there's an old open conjecture that this mixed language that contains the set of all words with an equal number of A's, B's, and C's is not indexed, and that's in this class, if I'm not mistaken, because you can recognize that with 3 counters or with.
But I mean, that's still open, though.
Yes, that's true. Yes. Okay. So that's true.
So slightly related, there's so Masaza has, I think, or maybe somebody else has something like blind multi-counter languages that also have holonomic functions, holonomic generating, growth series. Do you know? I mean, I don't know very well. Do you know about that?
So I know that the class RCM of Masadza have holonomic series, and they're equivalent to our class.
Mm-hmm.
The class LCL of Masadza also, RCM is Castillon and Masadza. The class LCL of Masadza is also equivalent with a pushdown when you add a class, stack, sorry.
Mm-hmm.
And they had a conjecture about some deterministic reversal bounding counter machines that are included into our class, because our class is equivalent to unambiguous reversal bounding counter machines. But I don't know, maybe there are other models I don't know about with also holonomic series.
Because I think some of, the Masaza languages have appeared quite naturally recently in group theory as sets of geodesics of virtually a billion groups. And so I wonder if your description, how different it is from some of those. Because the interest is to show that they have holonomic growth series. All right, well, maybe I'll ask you later.
Okay, feel free to send me a mail.
Yep. Mm-hmm.
Okay, we have to move to the next talk. Thanks, Florent. So the next talk is by Joel on the structure of solution sets to regular word equations. Go ahead, Joel.
Thanks. Okay, so yeah, thanks very much. This paper is by myself and Florian Manea on the structure of solution sets to regular word equations. So I'll just recap very quickly what a word equation is. So a word equation is an equation where on both sides we have words consisting of variables and terminals. So words over the combined alphabet of variables and terminals. And the idea is that in order to find solutions to this equation, we have to find substitutions for the variables for words over the terminal alphabet, such that what we get on the left and right hand side are the same word. So for example, we might substitute X for B and Y for ABA. This is a substitution, which we usually model as a homomorphism. And this is a solution to this particular equation because we get the same word then on both sides. And an equation is regular if each variable occurs at most once per side of the equation. And one of the nice things about regular word equations, and this is true actually for quadratic word equations, which is a superset of the regular word equations, is that we can represent the set of solutions, which might be infinite in general, as a directed graph. And in particular, we have a node which corresponds to our equation, which is kind of like a root. And then if the node containing the trivial equation with the empty word on both sides occurs in the graph, then we have a solution, and all solutions are represented by walks in this graph from the root to this trivial node. So our paper then considers the structure of these graphs. We try to describe the structure, and we also give some results on the diameter, on the size, and on their connectivity, or how DAG-like they are in the form of DAG width. And as a result of that, our main contribution is to show that the problem of deciding whether a regular word equation has a solution or not is NP-complete. And this is nice, I think, because it's a long-standing open problem and conjecture, I think, since the late 90s, that the satisfiability problem, so determining whether a word equation has a solution, is NP-complete in general. And this is one of the most general classes, I think, for which now this question is resolved in this way. So there are some classes for which it's known as polynomial, and a couple of other classes for which it's known to be NP-complete. But I think this is the now the most sort of large natural one in that case. And just before I open the floor to questions, I need to apologize. It was pointed out in the Slack that during my recorded talk, I said non-deterministic linear time, where I should have said non-deterministic linear space. So of course, if we can solve word equations in non-deterministic linear time, then this result wouldn't mean anything more than that. So thanks very much to the person that pointed that out in Slack. And sorry, that was just my mouth doing something different than what my brain was asking, I think, in that case. Thanks very much.
Thanks a lot, and thanks for the clarification. I was confused by that myself. And I checked the paper by Yesh, but he also seems to talk about linear time, right? In the title, at least.
So there's a paper around the similar time where he looks at one variable word equations where he solves them in linear time, but in deterministic linear time. But the result using recompression, that's for general word equations, this is non-deterministic linear space.
Okay. So are the questions to this paper? So there have been a couple of questions asked by Slack, and Anka had a question.
Yeah, so I can ask it directly. So I was wondering about what happens if you have systems of equations that are linear. So every variable occurs at most once in the equation. So if it occurs on one side, not on the other, but you have a system of equations. So do you know anything about the complexity?
Yes, so if you have, so there's two ways one can generalize a condition from a single equation to a system, right? We can consider the condition locally, so you just require that each equation in that system satisfies that condition, or you can apply it globally. So for example, if you're looking at linear equations, if you have a system that is linear globally, so each variable occurs at most anywhere in all of the equations, this doesn't get any harder than a normal linear equation, which is easy to solve. So it's polynomial in that case. But if you apply it locally only, so you might have lots of equations all containing the variable x, but it only occurs once in those equations, then this is actually as hard as the general case. So what you can do if you have any word equation, let's say we have a word equation and the variable x occurs 4 times, then what I can do is just replace each occurrence of x with x1, x2, x3, x4, and then add equations x1 equals x2, x2 equals x3, and x3 equals x4. So then we get basically the generality. But one thing that I would also mention in this regard is that in the paper, so not in the presentation, but in the paper, we do have a generalization of regular word equations to regular systems of word equations, and there our results hold. So we have some systems of word equations which can be solved in MP.
Okay, thank you.
Okay, are there some other questions? So I have a question. So you say that those solutions sets, well, the sets of solutions to word equations, if you look at the lengths, they don't form they're not Parikh sets or not definable Presburger arithmetic. Can you say anything about the structure of those sets? Are they definable in some logic and some fragment?
So the short answer is I don't know. So I know that there's at least one class that was considered where they showed that word equations with length constraints is decidable in this class because essentially so I think that there are some equations for which it's not Presburger definable, but it is definable in existential Presburger arithmetic plus divisibility. And there's a paper from a few years ago which shows that this is decidable, I think. But in general, I think it's open. So I don't know if there's any real sort of nice characterization or knowledge of what sort of logic you would need to express them.
Okay, thanks. Okay, if there are no more questions, then we can move to the last paper in this session. This is Georg will be presenting a paper on rational subsets of Baumslag-Solitar groups.
Yes, thank you. So I will share my screen. So, okay, yeah, I hope my screen is visible.
Yes, it is.
Okay, thank you, sorry. Yeah, so this talk is about rational subsets of Baumslag-Solitar groups, and if you're not familiar with this, essentially we look at, so one way of looking at this is its reachability in a weird type of Turing machine. So suppose you have a Turing machine with a with an input tape where the cells can contain zeros and ones. Then we have a machine that can go left, it can also go right, it can increment, and it can decrement. So what that means is if you're in the leftmost state, then you can go left, and then you can add. And then, of course, you change the 0 to the 1, and you can go left again. And if you then increase, you change that 0 to a 1. Then you can go right again. And when you now increment, then you increment like in a binary number, which means you turn the two ones into zeros, and you turn the 1 to the left of it into a 1. And then you can go left again, and then do a decrement. And then, of course, all these zeros turn into ones because you do a decrement. So the question that we address is, can we decide reachability? And you might ask, why do we look at these weird Turing machines? And that's because they're related to rational subsets of groups. So if you have a group, let's say a finitely generated group, then an automaton over that group is just a finite automaton where the edges are labeled by elements of that group. And this defines a subset, namely all those elements that you get by multiplying the elements of on accepting paths. And the membership problem is, if you're given a rational subset and an element, decide if that element belongs to the set. And if we look at this problem for a very specific group of matrices, namely those where on the left, top left component, you have some power of some fixed number q, and on the top right component, you have a rational number where the denominator is a power of q, then this is exactly the reachability problem I was talking about. So of course, now you might ask, why would we look at this weird group of matrices? Well, the reason is these groups, they belong to a class of groups named the Baumslag-Solitar groups, and they have a very simple representation. In fact, they're defined by a single equation, as shown here. And they often serve as counterexamples and are very prominent type of group among those defined by a single equation. So they've received a lot of attention from an algorithmic side in the recent decades. And another reason for looking at this class of at these groups is that there's a long-standing open problem, namely whether this rational subset membership problem is decidable for invertible matrices over the rational numbers. So decidability of the membership problem is well known for GL2Z, so for integer valued matrices. And just like the Baumslag-Solitar groups correspond to these Turing machines, you can imagine that GL2Z corresponds to a Bushra automata. So here reachability is well known. And a paper by Volker Diekert, Igor Potapov, and Pavel Semukin has shown that essentially these groups PS1Q are the simplest unknown groups between GL2Z and GL2Q. So they're the first ones to attack if you want to understand GL2Q. So our main result is that the rational subset membership problem for these groups PS1Q is decidable and p-space complete. And the second contribution is essentially how we did it. Namely, if you look at a configuration, then you can encode that as a word in a very natural way. You encode the pointer as a little accent, and you encode the initial position by a radix point. And then what we actually show is that for each rational subset, you can construct for the set of elements in the rational subset, the set of pointed expansions defined in this way is effectively regular. And then, of course, membership becomes decidable. And we show that the automaton is polynomial size if you allow for succinct representations. And maybe this new concept of subsets that have regular representations in this sense is at least as important as a contribution, because that's a very expressive set because it includes the rational subsets. It's very robust because it's closed under Boolean combinations, which the rational subsets are not. And this allows for a lot of applications. So for example, you can even decide emptiness of arbitrary Boolean combinations. So you can decide equivalence, inclusion, and so on. And you can also decide if a given rational subset is recognizable, which is an even smaller subclass. And that's typically a very difficult problem, deciding whether a rational subset is recognizable. So yeah, that's it. Thank you.
Thank you very much. Are there any questions? So I have a stupid question. So you say that the Baumslag-Solitar groups correspond to your weird Turing machines, and GL of 2Z corresponds to pushdown automata, does GL2, and with the rationals, does it correspond to some model of computation, a natural one?
That's a good question. If it is, then that would certainly be a more mechanical way of approaching the problem. I don't know. That's certainly a good question.
And are there other natural subgroups of this group which correspond to some well-known classes of automata?
I don't know yet. So the reason is essentially that for GL2Z, the reason that they correspond to push automata is that they have a finite index subgroup that is free. So getting from a group from an automaton over GL2Z to a push automaton is not really obvious. So the way the matrix operates is very different from the way the automaton operates. Whereas for these Baumslag-Solitar groups, that's a very immediate connection, as you can see in the full version of the talk. And I have no idea how to generalize this. So that's certainly an attack vector for the general problem. Yeah.
There's a question from Armin Weiss. Armin asked it on Slack, but maybe you can ask it here.
Yes. Can you hear me?
Yes. Hi,
okay.
Armin.
Hi. Yeah, nice talk. So I was wondering whether you can generalize these results to other Baumslag-Solitar groups. So for instance, if you have B as PQ where P divides Q. So is it still possible to get something out there, or?
I don't know. To be honest, we haven't thought about this, the case where P is not equal to 1 at all. That's definitely the next step. Yes. So I'll be happy to think about this. I don't think the results transfer immediately because it's not clear exactly how to represent the elements. So if you take this this Q-array expansion, then as far as I can see, if P is not equal to 1, then this is not a unique representation. You still have some equations there that you need to take care of. So I don't think it transfers immediately, but it's definitely a very good question.
Yeah. So I think if P divides Q, then you still have this this B as 1 Q over P sitting somewhere inside. So you have somehow these Q over P are numbers in there, but then there's something additional, something like which looks like a free group, but
yeah, we should definitely talk about this. I mean, you're more of an expert on these groups than I am, so let's do that.
Yeah, so I have no idea how one could attack it, but yeah.
Okay.
Are there any other questions? I have a silly question. What happens if you start with the empty type, so zeros everywhere, and you decrement? Do you get infinitely many ones to the left, or the machine breaks?
No, so I lied a little bit. The configuration can also contain a minus. So you can have a minus on the left. So if you decrement, then you just flip the sign.
Okay, yeah, sure.
But good question, good catch.
Okay, well, the time is almost up, but if there are any questions to any of the talks of the previous presentations, feel free to ask. But I see no questions, so in this case, I thank all the speakers of this session, and thank you for your attention and your participation. Thanks a lot.
Thank you.